Good afternoon and welcome back to Dr. Logic Awkwardly Does Logic. Unfortunately, it's come to my attention that the logic I've been doing was somewhat more awkward than desirable in the previous video because Zoom screwed up the recording of the whiteboard again. I really hope that between hearing what I've said and seeing what I did, what I wrote on the whiteboard that Zoom managed to record correctly, I hope that you can understand how the quantifier interchange rules work. If you don't, you can go to the link in the description of the previous video, go to the textbook, and you can see the definition and the schematic version of the rule there. So I really hope I don't have to re-record that video because I would much rather spend my time recording new videos like this one. So this is the next of the quantifier rules for predicate proof theory, and it's the easy rules. We'll start off with the easy rule for the universal quantifier and then do the easy rule for the existential quantifier. Which one is the easy one actually is symmetric. So we've got introduction and elimination rules for both quantifiers. In each case, one is easy and one is not really hard, but more complicated, we can say. And it's different in each one. So in the universal case, doing universal elimination is dead easy and straightforward. In the existential case, introducing an existential is the dead easy and simple one. And it has to do with what these sentences, what these operators are actually saying. So briefly, imagine you have a sentence with a universal quantifier. So for every x, px. What this is saying is that every object in your domain is P. In particular, what it means is that any constant that you have will pick out an object that falls in the interpretation of P. So anytime that you have a universal sentence, you can take off the universal quantifier, find all of the occurrences of that variable, and replace it with a constant. In fact, this just is uniform substitution. So there was a reason that we learned it. Hurrah! On the other hand, the existential introduction is basically where you go from, you point to some particular object and say, look, that one, that object, that one is P. It has this particular property. Once you know that you have some specific object that has a particular property, the existential quantifier allows you to step back and say, well, something has to have this property. So Sarah is giving this lecture, ergo something or someone is giving this lecture. So that is the idea behind these two rules. Now let me bring up my whiteboard, share it, make it full screen because that usually does the trick if it doesn't record properly. Hopefully this works. So the first rule that we're going to write out explicitly is the existential elimination rule. This is the one that says if for all x phi occurs on some line I of your proof, and tau is some term I occurs earlier in the proof than line n, then on line n you can write down phi with tau substituted in for the free occurrences of x. Now you remember that if you have something of the form for all x phi and you do a substitution instance on this, all of the occurrences of x are bound, and so nothing happens. The important step is that what we are doing is we take away the quantifier, and now all of the variable occurrences that had been bound by that quantifier now become free, and therefore are eligible to be substituted. So performing this substitution on phi will actually result in something. So you can write down phi with tau substituted in for the free occurrences of x. on line n with annotation universal elimination line I. So to get our lovely little schematic diagram, got your proof with some premises, and you've got some line I that says for all x phi. There's some annotation here, you don't necessarily know what. Then at this line here, line n, I can say, okay, well, if phi is something that holds of every object, well, then it must hold of tau. So there is my elimination of a universal. So you can do this as many times as you want. So, suppose you have a language that has the constants A, B, and C, then you can do universal elimination and substitute in A. Then you can do universal elimination and substitute in B. In fact, it's generally a good rule of thumb that if you have a universal sentence as one of your proof lines, do universal elimination for every constant that occurs in your premises. It will make your life a lot easier. How about then the other easy rule? That is the existential introduction rule. And this is one where, again, conceptually it's very easy. It's just the move from, if you know that some particular object is, has some property, then you can take a step back and make the weaker claim, well, some object has this property. The schematic version of this that I write down is going to involve the same sort of abusive notation that I mentioned when I was talking about the substitution of identicals rule. So in a sense, we will be substituting variables in for constants, which is not something we formally defined, but which I trust all of you will be able to kind of make the extrapolation and understand what I mean just with this shorthand notation. But let's write out what the rule says. So the rule says that if phi, which has tau in it, we don't necessarily say when or how or what, or even what kind of term tau is. It could itself be a variable. It could be a constant. It could be something else. So if phi tau occurs on some line I of your proof, where phi is a formula, tau is a term, I is earlier in the proof than line n, then exists x phi with, and here's the abusive notation, I'm saying substitute x in for tau. Now tau itself might be a constant, it might not be a variable, so formally speaking you can't do this, but what I mean just with this notation is find every place that tau occurs and replace it with x. So this can then be written down on line n of your proof with annotation existential introduction on line I. So let's draw our little schematic proof down here. We've got some various premises, got some other things. Line I, you've got this formula that happens to have this term tau in it. Some annotation, we don't know what, but we do know that at line n, I can stick an existential quantifier on the front. I can write down the result of erasing all occurrences of tau and writing x down instead. That's how you can read this with the annotation existential introduction, line I. See, very easy. All you need to do is some rewriting of your formulas, either putting constants in where you had free variables, or taking constants out and replacing them with variables, which become bound because you add the quantifier. The introduction rule for universal statements and the elimination rule for existential statements are both somewhat more complex. I mean, they're not hard, not in the way that, certain things can be hard. None of these things that I'm giving you in these rules are all that difficult. They just take a little bit of time, a little bit of care, and some attention. So there will be particular things that you will want to check just to make sure that you're applying those rules correctly. But so long as you do that, you won't have any problems. But they are complicated enough that I'll do a separate video for each one of them. And then after that, we will finally be able to start putting all of these rules together and doing some practice proofs. Yay! So, join me in a bit. Take care. Cheers.